In this recording, I'm going to present a review of three-dimensional solutions to the time-independent Schrodinger equation. I expect that most of this material will be a review of material that you saw in Quantum Physics 1, but in order to make sure that the class is all on the same page together, I'm going to take a little bit of time to review this. I'll start by talking about a three-dimensional cubical well, a rectangular well, in Cartesian coordinates, and then shift off into solutions for spherical potentials with spherical symmetry, with no angular dependence or time dependence, and discuss the concept of angular momentum and calculation of wave functions that include angular components, and then finally come back and talk about the explicit solution for the Coulomb potential. So the three-dimensional rectangular box is a situation like this. Essentially, we're going to define the potential inside the box to be 0. So the potential is 0 inside of the box, length Lx, Ly, Lz, for example. And the potential is going to be infinite otherwise. That is, the particle is going to be confined to be inside of the box. The standard approach to problems like these is to assume that a product solution exists. That the wave function is a product of an x as a function of x, y as a function of y, z as a function of z. And plug that into the Schrodinger equation. So here is our overall Schrodinger equation. The potential as a function of position is buried in here, and we have assumed that this is time independent, so there is a single energy for this state, no time dependence to the energy. The standard solution, we separate each of the terms in x and in y and in z from one another, and that is done by dividing this product solution situation, the Schrodinger equation with the product solution, by the wave function x, y, and z. And this leads to a separation of the x term, the y term, and the z term. And what we have done here is to take the component of the potential along the x-axis. There is no component, it's not a vector. Sorry, what I mean is to take the profile of the potential along the x-axis. So for example, over here, the potential is infinite for x less than 0, so infinite here, then it comes down, it's 0 in the box, and then it's infinite outside the box on the other side. And so we've just broken the potential into the potential along each of the three dimensions. So it's a profile of the potential, and then the energy. And what we've done here is to multiply through by 2m over h bar squared in order to separate the functional dependencies here. The standard approach is to pull all terms that have to do with z over to one side of the equation, and this relationship can only be true for all x, y, and z if the two sides are separately equal to a constant, and we assume that those two sides, that constant in this particular case we're going to label E sub z. And that's what we have done here. So the differential equation that we have that remains is this one here, function of z, the profile in the z direction of the potential, and the energy for the problem E sub z, the constant E sub z, as the solution. Continuing to solve that z equation, what we typically do, what is frequently done, is to collect many of the constants together into a wave number, k sub z, which is equal to the square root of twice the mass of the particle divided by h bar squared, times the difference between the constant E sub z and the potential V sub z. So this has units of inverse length. And then for this particular problem, the solutions are harmonic functions, or exponentials if you like, but I chose harmonic functions in this particular case. A constant times sine kzz, and another constant times cosine kzz. And the constants here will depend, and kz will depend upon our boundary conditions. The fact that the wave function must go to 0 at the z equals 0 boundary gives us the condition that the constant b must be equal to 0. The fact that the wave function must go to 0 at the z equals L sub z boundary, that's the size of the box, boundary, gives us the condition that k sub z must be equal to an integer times pi over L sub z. And remember, this is actually not a condition here, but we defined k sub z as the square root of 2m over h bar squared ez minus vz. So just pulling that back out and knowing what kz must be, we discover that the E sub z is quantized, and we'll assign a quantum number to that, n sub z, which we had up here. And so the solution to this equation has quantized energies. Now we return to the x and the y portion of the equation. We've already separated the E sub z solution. Perform the same separation again, putting all terms in x on one side, all terms in y on the other side. In this particular case, we chose to collect all the constants together on the x side. It's not particularly important which way we choose to do that. The only way those two sides can be equal to one another for all x and y is if they're equal to a constant. We choose that constant to be equal to this. And then solving the y side as we did for the z side before, we end up with the same sort of relationship with a constant, or rather with k sub y equal to an integer ny pi over ly, with then the energy being equal to h bar squared ny squared pi squared over 2m ly squared. Just like the situation for a particle in a box that we solve for a one-dimensional box. But this is the second dimension of a rectangular box, rectangular prism box. Now we've got everything that we need in order to address the x problem, the x solution. We're going to define E sub x so that E sub x plus E sub y plus E sub z is equal to the total energy for the problem. Go forward and solve that in exactly the same way, exactly the same situation with respect to the boundary conditions, and we find out that E sub x is equal to h bar squared k squared k sub x squared over 2m, and k sub x is quantized, integer n sub x times pi over lx. And when we put that all together, then to find the total energy for the problem, we find that the total energy is equal to h bar squared pi squared over 2m times the sum of the squares of the energies that come out of each of the specific directions. So I've got three lengths here, length in the x-axis, y-axis, z-axis, and three quantum numbers, three integers squared, which yield the total energy of the problem. And remember that these n sub x, y, and z here also determine what the functions are that describe the total wave function. Remember that the total wave function is the product of the x wave function, the y wave function, and the z wave function. In summary then, for this three-dimensional case, it is a three-dimensional problem, and we just found out that we have three space quantum numbers that appeared, and x and y and z. We're now going to look at the particular shape of the box. If the box is a cube, so I know this doesn't quite look like it, but if the box is shaped like a cube, then we go ahead and solve for the energies of the particles in the box, for a particle in the box, and we find when n is equal to 1, and x and y and z are equal to 1, each equal to 1, we have a particular energy, right? For the case where n, x, and y and z are not the same, where two of them are 1 and the third is 2, then we find that we get the same energy whether the n's are 2, 1, 1, 1, 2, 1, or 1, 1, 2. This situation here is called a degeneracy. We have three states, three separate quantum states of the system that happen to have the same energy. They have the same energy because the sides of the box are equal in the x, y, and z direction. If we now change the shape of the box so that one side is different in length from the other sides, in this case I think we make the c axis a little bit shorter than the other axes, so AAC. All right, we make the z axis shorter. Then we find that when we go to the 1, 1, 2 versus 2, 1, 1 state, they have different energies, because remember that the energy depends upon n squared over L squared for each of the directions. And the word that we use to describe this is that we have split the degeneracy. We have broken the degeneracy. This degeneracy occurred because of the symmetry of the problem, AAA, and that degeneracy is broken when the symmetry of the problem changes. So we changed one of the directions, sizes in the direction, and the energy levels split. If we have three different axis sizes, then we end up splitting those energy levels out. And in a little bit, we're going to be looking at solutions to spherical problems, and a way in which degeneracies are broken there is to apply electric fields, external electric fields, or to apply external magnetic fields to a problem. And then we look at how energy levels shift around and split, and degeneracies change. And when that happens, then we can determine something about the symmetry of the states that we were looking at and the nature of the states that we are studying. One of our tools for studying what happens in a quantum mechanical system is the experimental tool, which involves looking at the light that comes out of a plasma, for example. So in a plasma, what we might do is excite ions or excite atoms in a system to create ions, or to excite electrons within an atom, and then look at the light that comes out of that system. So we might apply an electric field, an oscillating electric field, and cause the atoms to ionize and electrons to bounce around and interact with the atoms and ionize other atoms. And then we look at the light that comes out. And what was observed before quantum mechanics was even thought of was the series of quantized transitions, very specific transitions. So this is the hydrogen atom here, and what in particular was observed were a series of wavelengths. 1215.68 nanometer wavelength emission, 972.54. Oh, these are angstroms. I take that back. This would be hundreds of nanometers. So this is in the ultraviolet. And this particular series is called the Lyman series, observed by Lyman. And then the Balmer series was studied by Balmer. And these happen to be mostly in the visible here. So this little set in here are visible transitions. And then there are infrared transitions that were observed as well. So all of this was seen before the theory that we're about to talk about. What was observed was that the energy of the photons that come out of this system fit a pattern. They were equal to 13.6 electron volts times 1 over an integer squared minus 1 over another integer squared. And that's sort of a neat thing to observe, that there was this pattern of integer ratios. And again, that was worked out So now we're going to address the theoretical solutions, first for central potentials, and then we'll specifically go to the Coulomb potential. The three-dimensional time-independent Schrodinger equation is this: a kinetic energy term and a potential energy term and a total energy. In spherical coordinates, that Laplacian leads to this long and messy equation, and psi is our wave function, and r is the distance from the origin. Theta is the angle measured with respect to the z-axis, and phi is the azimuthal angle. We assume that that solution to this particular problem can be expressed as a product solution. R is just a function of radius, theta a function of theta, phi function only of phi, and plug that in. And so this is just rewriting the Schrodinger equation again. We assume, by the way, that the potential is time independent in writing this. Now we're going to make a number of assumptions that are going to allow us to look at specific behavior of the solutions to this equation. Number one, and most important, we assume that the potential is purely a function of distance from the origin. There are no angular dependencies to the potential. And then we're going to go ahead and divide this Schrodinger equation through by the product function r theta phi. And we're going to move the variables around in order to isolate one of the terms, the azimuthal term in this particular case. So basically, these are the operations that we are performing, and our Schrodinger equation becomes this. I had a 0 on one side, but now what I've done actually is to pull the phi equation over to one side, leaving theta and r behind. The only way that this can be true for all r, theta, and phi is if the two sides of this equation are equal to a constant. And I've chosen, because that is the convention, to set that constant equal to m sub l squared. And the phi equation, just this portion here, now has relatively straightforward solution, e to the plus and minus I m sub l phi, where m sub l is an integer. We're left with the other two variables now. We're going to separate the angular terms from the radial terms. And while we're at it, we'll keep the constants, stray constants in energy, for example, over here on the left side with the radial terms. But we'll leave the m sub L constant from the previous solution over here on the angular side. And in order for those two sides to be equal to one another for all r and theta, they must be equal to a constant. And for reasons that will not become clear later on, but are the convention that have to do with the solution to the Legendre equation, right? We're going to set the constant equal to an integer L times the same integer L plus 1. So L times L plus 1. The angular part of Laplace's equation, that is this bit over here, is called the Legendre equation. So I just separated it out here so you can see it. And typically, so remember that the thetas here came out of the fact that this was spherical coordinates, but the Legendre equation can simply be solved with variables. So we're going to make the substitution to make it look like the standard form of the Legendre equation, where we make the substitution x is equal to cos theta. This is not the Cartesian coordinate x. It's just a variable. Do a little bit of arithmetic here and convert this equation into this one. And then in standard form, the Legendre equation looks like this, where the solutions are these thetas. The solutions to that particular equation are actually called the associated Legendre polynomials. So the solutions for any problem with central potential are associated Legendre polynomials. We're not going to solve that problem. It's a hard one. You can find a good step-by-step solution to the Legendre equation in Appendix B2 in Townsend, and more steps in the textbook by Iceberg and Resnick in their Appendix N, I believe it is. So Iceberg and Resnick, Appendix N. But the Townsend is not too bad. It's pretty good. So we're just going to solve here for the Legendre polynomials, which correspond to the special case when m sub L is equal to 0. So take the Legendre equation and set m sub L equal to 0. And you end up with this differential equation, and the solutions to this differential equation we've written here as P sub L, right, are called the Legendre polynomials. So the other solutions with m having arbitrary values are the associated Legendre polynomials, integer values, and the solutions with m equal to 0 are the Legendre polynomials. These polynomials appear as solutions to many physical problems. In particular, Legendre polynomials show up in mechanics and in electromagnetics. So it's a good idea to get a little bit of idea of what they are now. Here are some properties of the polynomials. Okay, remember that this is a function of x. Legendre polynomial is a function of x. There are a whole bunch of coefficients. The polynomials can be expressed as the sum of terms in x to a power. So it's a power series assumption. This is what Legendre did, was he assumed a power series solution and then found the coefficients for the power series solution that depend upon L, so P sub L, and a sum over terms in order to actually get the power series. And this power series terminates, so it starts at j is equal to, because I've got a j in there, it starts at j equal to 0, and goes up to L over 2 for an even L, and L minus 1 over 2 for odd L. That should be odd L there. The first few Legendre polynomials actually are P0, so L equals 0, is just a constant 1. P1 is x, P2 is 3x squared minus 1. Okay? Remember, we made a substitution, x is equal to cosine theta, so I've just written this out all again, explicitly putting the cosine thetas, P of theta now. That just happens to be the first three, and you can generate any order that you like using this relationship. Legendre polynomials form a complete orthogonal set of functions on the region from x equals minus 1 to 1. That means that we can express any function over that interval in terms of Legendre polynomials, just as we were able to express a wave, a periodic wave in space, as a series sum of sine and cosine functions. We can do the same with Legendre polynomials for this bound where the function repeats as you go around in theta. So cosine 0 is 1, cosine pi is minus 1, and so this function repeats upon itself. The normalization and orthogonality conditions for Legendre polynomials are that the integral from minus 1 to 1 of the product of two Legendre polynomials is 0 if they're not the same polynomial. That means that they're orthogonal, and has a value of 2 over 2n plus 1, where n is the order of the polynomial otherwise. So if you brought that 2n plus 1 over 2 to that side, then this would be normalized. The associated Legendre polynomials, as I mentioned, are the solutions to the wave equation, to the angular part of the wave equation for non-zero m sub L. I say we're not solve the m not equal to 0 case now. No, we're not going to solve it at all, ever, in this course. But we state the relationship between the Legendre functions and the full solutions, the full solutions being the associated Legendre functions. So theta sub Lm, where now m is not 0 any longer, is related to the L Legendre polynomial in this way. P sub L is Legendre polynomial. And so then using this and our relationship for the Legendre polynomial, we can find any order of L and M for the associated solutions. One thing that we can just observe here is that any terms for which M is greater than L, remember that L will lead to the order of the polynomial that we're, of the Legendre polynomial. L equals 0 is a constant, L equals 1 has got only x in it. So this is the order of the polynomial. If I take more derivatives than there are orders, then this term is going to go to 0. So these things are only defined for m equal to or less than L. These functions have been represented in a variety of ways, and I've just got a couple of examples here. Here are some figures that are taken out of Crane that attempt to give you some representation for what the wave functions the angular portions of the wave functions look like. So this is a representation that tells you that the wave function is the same all the way around the angles surrounding the origin, and that the shape of the wave function changes because, for example, we've got a cosine theta squared in there. The shape of the wave function changes as we change L and M. So here are some examples. Here's another way of representing those wave functions. L is equal to 0, L is equal to 1 here, and the L equal to solutions are here. This is taken out of one textbook. This is taken out of the textbook that I'm recommending to you. And then there are three-dimensional images that can be rotated at the website hosted by Falstadt. If we put the angular solutions fully together, that is, that we take our associated Legendre polynomials and our solutions to the phi equation with the integer m, and then what we're going to do in addition is multiply by some normalization factors, all right, so that we form what's called a spherical harmonic. Sometimes this is written as y sub Lm, sometimes as y sub L superscript m. These, no matter how they're written, are the spherical harmonics. So here, again, I've written y sub Lm. Here it's y Lm. This complication over here is to ensure that when we take the product of one spherical harmonic times another spherical harmonic integrated over the angular part of the volume in a three-dimensional space, so integrated over the angles, that integral will be equal to 1 if L and L prime and M prime are each separately equal to one another. L equals L prime, M equals M prime. And here are some of the specific. Now we take that and put it here. It looks to me as though I lost a square root here, so I will take another look at that to see whether I've lost or gained a square root. I see a square root down here that seems to have disappeared over there. So I think there's a square root of 4 pi. I will check that. But these are the spherical harmonics, and spherical harmonics should be such that when you integrate over the angles, the integral is 1. Now we can worry about the radial equation. Up until now, we have paid no attention to the actual potential. We didn't specify the potential, in fact, other than to say that it depended upon distance from the origin only. And so everything that we've done so far as the angular solution applies to any problem that has spherical symmetry. But now we're going to get specific. Remember, R is the radial portion of the wave function, and the arithmetic becomes a little bit easier when and remember the angular portion is the L times L plus 1. The arithmetic becomes a little bit easier if we set a new variable u of r equal to the product of the variable r times the function capital R of r, right? So when we do that, the Schrodinger equation reduces to this form. And the other thing that we've done in going from here to here is to explicitly put in the Coulomb potential for an electron with a proton. So this is now the potential for an electron on a hydrogen atom. We do a little bit of scaling here. We end up with an equation that looks like this. And actually, once again, we would seek solutions that are series solutions. And we'll talk a little bit about the approach to that, but I'm not going to go into too much detail here. This in itself could take more than a few classes to go through the detailed solution. I consider that to actually be more of a math class thing than for an overview class like Quantum Physics 2. However, the solutions to the radial equation are worked through in detail in the textbook by Iceberg and Resnick. So I recommend that book is essentially for free out there as PDFs. I recommend that you get a copy of it. I actually recommend that you get a new hard copy of it because you will refer to it frequently. It's just at a slightly wrong level for this particular course. All right, now some special situations. Let's look first at angular momentum equal to 0. So L is equal to 0, and with the assumption of the Coulomb potential that we've had so far. So first of all, we'll look at that equation that we were just looking at, that we were just talking about, in the very large R limit, in which case terms that have got 1 over r squared are going to disappear from the equation, and we just end up with this relationship here to work through in order to try to solve for u. Remember, rho is just radius scaled to the Bohr radius. This is the energy measured with respect to the electron being at infinity, and electron and proton attract one another, so this energy is negative. The solution to this equation is u proportional to e to the I square root of epsilon rho. And because the energy is negative, that's actually exponentially decreasing in distance from the origin rho. Now remember that that is u, and u is equal to rr. So there is going to be a variable r that appears in the final solution. All right, remember that E is negative. So this is just in the extreme case of very large R, all right? And in that case, the equation is going to be dominated, the relationship is going to be dominated by this exponential decay. We then can go back to the original full equation and attempt to solve it with a polynomial expansion. And we find that the lowest order polynomial that has the right behavior as rho goes to 0, all right, is u of rho is equal to r e to the minus square root of energy, absolute value of energy, times rho. These solutions look like this. These are the actual wave functions here now. And the wave function just happens to be normalized at the origin here. Right? We're just dividing by the magnitude here. That wave function as a function of r decays exponentially away from the origin. And if we take the product of r times that wave function, then we get a shape that looks like this. This is the solution u of r that we just found. When we put that u of r in to the original wave function, Schrodinger equation, we find that the first energy state is this bunch of constants, which comes out to be approximately minus 13.6 electron volts, or 1 Rydberg. For L equals 0, we can continue to look for higher order solutions to the equation, to the differential equation, keeping that e to the minus rho over 2 in there, okay, keeping that. We can look for those solutions, and the polynomial portions of the solutions look like this. I'm missing a constant in this term here. There's an energy in there, okay? So that's the next order equation. The first one just had one row. This one has got its second order, third order in row, and so on. These are the relationships that solve the differential equation. And we find that the energies that should be up here are equal to the original Rydberg energy divided by n squared. And there are some examples of what the functions look like. I want to go back and talk a little bit about angular momentum at this point. In classical physics, the angular momentum of a particle is defined as r cross p. And we have operators in quantum mechanics for those vectors, r and p, right? The operator for r is xi plus yj plus zk in Cartesian coordinates. And for p, it's ih bar d by dx I plus ih bar d by dx d by dy j, and so on, all right? So we go through and do the cross product, and we find out that L sub x, the angular momentum about the x-axis, is equal to ypz minus zpy. And as I said, these are operators. So down here, I actually went ahead and put the operators in for each of those terms, right? The magnitude of the angular momentum is, because there are three components here, and that they're orthogonal to each other, Lx squared plus Ly squared plus Lz squared. Right? And L is a vector, and so I've just picked up a component of the vector here. We can rewrite the angular momentum in terms of operators, which I've done here. And we know then from this and this that the square of the overall angular momentum, the total angular momentum, is the square of the angular momentum around the x-axis, around the y-axis, plus around the z-axis, all right? And when we put those operators together and convert into spherical coordinates, we find that the square of the angular momentum operator that comes out of going through these classical steps here is equal to the angular portion of the Schrodinger equation. This is what we solved for a little bit ago. And so the angular portion of the Schrodinger equation is really just L squared operator operating on the wave function. That's it. Here's a reminder here. The angular term in the Schrodinger equation is this bit here. I've brought back in the 1 over r squared from the original Schrodinger equation. And so we can rewrite this portion of the energy in the Schrodinger equation as angular momentum operator squared operating on the wave function divided by 2m r squared, distance from the origin. That is the rotational kinetic energy of the system. So our solution to the angular term produced the rotational kinetic energy, and that is related to these L times L plus 1 terms, the angular momentum. The magnitude of the angular momentum is quantized, And the projection onto the z-axis turns out to be quantized as well as we work through that. So if we put all of this together with the rotational kinetic energy, the translational kinetic energy, and the potential energy of the problem, and solve for the energy levels of the hydrogen Coulomb system, we find that for a principal quantum number n equals 1, that is the lowest order in radial solution, that the radial probability density looks like this. There's one lobe in the radial probability density for this state here. For the next state up, I have one antinode and no nodes in R in the function itself. For the next state up, n equals 2, there are 2 nodes for the L equals 0 state. But in the angular momentum, we can find that there's another term here where there's one node in R and one node in L. So an interesting situation, which just occurs for the Coulomb atom, Coulomb potential alone, is that for the n equals 2 state, the energy of the L equals 0 state is the same as the energy for the L equals 1 state. The radial portion of the wave function has changed, and as a result, the portion of the energy which is associated with the radial wave function has decreased. But the amount of energy associated with the angular portion has increased. The angular momentum has increased, and the rotational kinetic energy has increased in just such a way to compensate exactly for the loss in the radial energy. And the same here. These degeneracies, the fact that this state is equal in energy to that state, is coincidental. It's due to the fact that the potential is a Coulomb potential. If the potential is not Coulomb, which would be the situation for anything other than a simple single electron on a proton or on a nucleus, a single electron on a nucleus. If it were anything other than that, we would not have this accidental degeneracy, and there would be a splitting of those two states. I showed you representations of the wave functions previously, and just have these again to remind you that this is a representation of what the density as a function, what the symmetry of the density as a function of angle is for each of the different angular momenta. I want to remind you that much of the theory that we've been working through was originally stimulated by the observation of optical transitions. So it was experiment that led to the theory. And there's a little bit more with respect to spectroscopy that I want to mention now, and that is that only certain transitions were observed. So for example, we don't see a transition between the 4D and the 3D, or the 4P and 3P states, which I'll be talking about this spectroscopic notation in a little bit. There are some transitions that we don't see and some energies that we don't see. The probability of a transition actually occurring also turns out to be related to the symmetry of the initial and final states, and the mechanism by which the transition occurs. We're going to talk quite a bit more about that in a little bit. One of the experiments that begins to tell us something about what is going on in the atomic systems, was originally known as, it is, the Stern-Gerlach experiment, in which atoms were sent out of an oven just to give them speed, but they were traveling through vacuum and were sent through a slit and actually sometimes velocity selected, but in this case is shown that they're simply traveling through space, and in the absence of, with suitable slits, in the absence of any magnetic field, we would just see those atoms travel straight through, and we get an image of the slit on the other side if we had a point source here. And when we apply a magnetic field, and that magnetic field is non-uniform, then it will turn out that there's a net force that is exerted on a magnetic dipole. So if I have a dipole with magnetic moment mu, and that dipole is moving through the magnetic field, along through the magnetic field, then if there is a uniform magnetic field, there's no net force on the dipole. But if the magnetic field diverges, there will be a force on the dipole. And so the thinking when they did this experiment originally was actually that if electrons in atoms had angular momentum, then those angular momenta would show up as dipole moments, and they could measure the magnitude of the dipole moment by looking at how far the atoms were diverted upon passing through this magnetic field. So that is the basic idea, all right? And now the question is, what is actually going to be observed? If the angular momentum is 1, we expect 3 separate lines do the projection of the angular momentum onto the z-axis, the axis of the magnetic field. 3 possible projections, 3 separate lines. What's actually observed is 2 lines. For example, for the angular momentum 0, there should only be 1 line at the center. In the absence of the field, it looks like this. You apply the field, and there only 2 lines are observed. Now, because of the non-uniformities, it's just sort of a splitting that occurs here. That was a bit of a shock, and seemed to indicate that our thoughts about angular momentum were incorrect. For one, when we had an atom in an L equals 0 state, there should be no angular momentum, and so there should be no splitting. But in fact, there was a splitting into 2 lines. That led to the idea that perhaps electrons themselves have spin, and we'll be talking in future courses, in future classes of this course, a bit more about the spin of the electron. So this experiment and some other theoretical ideas led to the idea that electrons somehow have spin, and that spin gives rise to half-integer angular momenta of some sort, magnetic moments. The new spin number, m sub s, was proposed, and it's got a value of angular momentum equal to h bar m sub s, and can take integer values, right? However, it will be found that, not integer values, it varies by integer amounts, and that the spin of the electron is 1/2, with projections onto the magnetic direction of plus 1/2 or minus 1/2. So when we're talking about magnetic moments, angular momentum gives rise to a magnetic moment, and the spin of the electron gives rise to a magnetic moment. And by looking at how atoms shot through diverging magnetic fields split upon arrival at a screen, we can learn a lot about the original magnetic moments of the atoms. With this slide, I'm going to stop this portion of the lecture. There are more slides in this package. There are several more slides in the package, and I'm going to give those slides as a later portion of the lecture. So it will be on the same day, but this particular lecture has now run 1 hour. So I'm going to split the lecture into 2 pieces.